Hi guys, I wanted to make a video on another really common dynamics problem, which is when you have, thanks bird, which is when you have a system of two blocks with one block on the bottom and one block on top of it, and there's no friction between the ground, but there is friction between the two blocks, and the block on the bottom is being pulled by an applied force. Okay, so in this problem, we're going to solve for the acceleration of the system and also the applied force acting on the block. So let's first solve for the acceleration of the system. Okay, so the first thing that we're going to do is we know that because these two blocks are acting together and they can be thought of as acting in one system, each individual block must have the same acceleration if they're moving together. And so what I'm going to do is I'm only going to look at my block on top. So if I sketch a free body diagram for my block on top, okay, so it's of mass little m. So of course I'll have my force due to gravity acting from the center of mass on the block down towards the ground. That's just the block's weight. And then, of course, I'll have a normal force acting orthogonally from the surface on the object. So that's my normal force. And then something that can be a little tricky about this problem, about these types of problems, is noticing that we do have a frictional force between the two blocks. And when you think about it, we would have to, or else this block would just slide right off when our bottom block was pulled. But because of our force of friction, it's able to move with the block. So something to think about is that when we start pulling our lower block, this is our direction of motion and the direction of our applied force. Well, when we think about Newton's first law, the law of inertia, we know that an object at rest wants to remain at rest. So because our block at the top was initially at rest, because of inertia, it'll want to slide in the direction opposite of our motion. So therefore, because we know that friction opposes motion, our direction of static friction will actually be going or pointing in the direction of the motion of the system in this scenario because of inertia. So that's the direction of our force of static friction only for our block on the top. Okay, so now that we've sketched our free body diagram, we can actually get started solving for the acceleration. Okay, so I'm first going to write out that my sum of the forces in the x dimension, well, this has to be equal to mass times acceleration because my block is accelerating in the x dimension. And then my sum of the forces in the y dimension, well, my little block isn't like levitating or crushing down into my bottom block, so these forces are canceling out and they're equal to 0. So in my x dimension, well, I know from the diagram I drew that the only force acting in the x dimension is my force from static friction, and that's equal to mass times acceleration. Okay, so now in my y direction, I know that my weight must be equal to my normal force, and we know that weight is just equal to mass times gravity, so that's my normal force on the little block. And my little block is of mass little m. Okay, so now I can write out or define my force due to static friction. So we know that that's mu times the normal force, and this will equal mass times acceleration, and we just solved for the normal force with it, which is just mg. So we know that mu times little m times g equals little m times acceleration. I can cancel out an m from both sides, and I get that acceleration is just equal to mu g. So now we know what our acceleration is, and that's equal to mu g. Okay, so now we solve for the acceleration of the little block, and therefore we know the acceleration of our whole system. Okay, so now let's solve for the applied force. And there are two ways that we can do this. There's kind of a harder way and an easier way, but I'm gonna show both. So we'll start with the way that's probably a little more difficult to conceptualize. So what I'm gonna do is I'm going to isolate now my lower block, or my block of mass capital M. Okay, so I have my lower block. Now let's think about the forces acting on this block. Of course I have the weight of my block of mass capital M, but now I also have the weight of my little m times g, or I'll say weight of little m. And then I have the normal force of my capital M. And then I would have the normal force, of my little m block. So those are my forces acting in the y dimension. And then, of course, we know from the diagram that we have some applied force acting on it to the right. Okay, now this is where things can get a little bit trickier. So we know that the surface on the top of this block is frictional. And we know that this little block of mass, capital M, well, it wants to slide this way. So its force of static friction is acting that way. However, this block is moving to the right, or we can even think of it as being a stationary block on top of it, because relative to our block of capital M, the little block on top isn't moving. It's staying stationary on top of this block of capital M, and our whole system is moving. But because we have an applied force acting to the right, and well, we have a surface up here that's frictional, friction will oppose motion. And so, therefore, because I have this frictional surface, I'll have this same force of static friction that's acting on my little m, just acting in the opposite direction. Because while my little m wanted to slide to the left, so therefore the force of static friction was acting to the right, my capital M is being pulled to the right, and that's my direction of motion. So now this force of static friction on top of the block will be pointing to the left to oppose motion. So I do think that's kind of the trickiest thing to notice in these, but when you really think about it, having a frictional surface on the top of the block is no different than if this ground was frictional and we had some force of friction acting on the ground. Now, of course, that would be kinetic friction because it would be moving, whereas on the top, because this block is staying stationary, it's actually static friction, but friction will act the same way, or conceptually the same, no matter where our frictional surface is. So I hope that makes a bit more sense as to why we would have our force of static friction being the same but pointing in the opposite direction for my lower block. Okay, so now let's actually get started with solving for my applied force. Okay, so I know that my sum of the forces in the x will equal mass times acceleration, which we solved for earlier. And I know that my sum of the forces in the y will just equal 0. Okay, so let's just start thinking about the x dimension first. So I know that my positive, I should really add a coordinate system to this. So I'm saying this is my positive x direction and that's my positive y direction. And the same goes for my little m. Okay. So, therefore, I know that my force applied is acting in the positive direction, and then I know that I'm subtracting this force of static friction that we calculated in the previous example, and that's going to be equal to my block of mass m, I'll make this look more like our capital M, times acceleration. Okay, so then I can just rewrite this as my force applied being equal to my capital M times acceleration, plus if I add force of static friction over, plus my force of static friction. So then I know that my force applied is just equal to capital M times mu, so weird looking mu, times mu g, plus, well, let's look at what we calculated earlier for our force of static friction. That would be right here. And we know n there is equal to little m g. So I know that this is equal to mu times little m times g. So now if we wanted to clean this up, we would just get that mu g, which I can plot of both of these, is times big M plus little m, is equal to my force applied. Okay. So that's one way to solve for our applied force, but there is also another way which might be a bit easier that doesn't require as much kind of brain power. Okay, I'll put this over here. Okay, so my second way, to solve for my applied force is to look at this big M and little m block as just being a system. So let's imagine if this was just all one shape that was kind of fused together. Because, like I said earlier, relative to the lower block, the little m block isn't moving. So we can think of this, because this little m is kind of locked in place on top of my capital M block, we could think of this as just being all one object like I've drawn here. So then we wouldn't have to worry about our force of static friction, and we can just say our force applied. And then if I were to draw, I would have the weight of big M plus little m, and then I would just have the normal force canceling that out. So now what I can say is, if I actually were to sum up the forces acting on these blocks, or this one block, I could say that my sum of the forces in the x is equal to my m total, so that'll be big M plus little m times my acceleration, and then my sum of the forces in the y will stay equal to 0. And so what I can just say then is that my force applied is equal to my big M plus little m times mu g, which is my acceleration. And that is just my force applied. And we can see that my force applied here is the exact same answer as what I got there. And so this is kind of an easier way, I think, to think about finding the applied force. Both ways work, but as you can tell, this second way was obviously a lot quicker. So that is how we solve a problem like this. I hope this video was helpful, and I'll see you in my next video.